So here's the next one. Now, for this one, in order to recognize it's telescopic, you've got to have it in the form of two fractions added or subtracted together. So when you see this one large fraction right here, you're going to want to use your partial fraction decomposition to write this larger fraction as a sum or a difference. So remember your partial fraction decomposition, I'm going to take 1 over k times k plus 1 equals a over k plus b over k plus 1. So I need to solve for those numerators. So I know when I multiply by the LCD, 1 is going to be equal to a times k plus 1 plus b times k. And that's where I'm going to let k be equal to 0, k be equal to negative 1 to get this to cancel. So if I plug in 0 for k, that's going to go to 0. 0 plus 1 is 1, so 1a equals 1. So I know that a is equal to 1. When I plug in negative 1, negative 1 plus that goes to 0. Negative b is equal to 1, so b is equal to negative 1. So now I can rewrite my series as k is equal to 1 to infinity. Instead of writing it as one larger fraction, I can break this up into my two smaller fractions. So 1 over k minus 1 over k plus 1. So now I can write out my first few terms. So when I plug in 1 for k, that's going to give me 1 over 1 minus 1 over 2. Plus, plug in 2 for k, 1/2 minus 1/3. Plus, plug in 3 for k, 1/3 minus 1/4. Plus, 1/4 minus 1/5. So now let's see what, here's a negative 1/2 and a positive 1/2, negative 1/3, positive 1/3, negative 1/4, positive 1/4, and so on. So it is going to converge by telescopic sums. And the only term that's remaining is the very first term, which is a 1. So it converges to 1. So here's my 1 over n plus 2 times 1 over n plus 3. Again, I need to see if this is a telescopic sum. I need to break this larger fraction up into my partial fractions. So I can write this as a over n plus 2 plus b over n plus 3. Again, when I multiply everything by the LCD, that's going to leave me with 1 is equal to a times n plus 3 plus b times n plus 2. So I'm going to let n be equal to negative 3, n be equal to negative 2. So when I plug in negative 3, that'll go to 0. So negative 3 plus 2 is a negative 1, so I know b is equal to negative 1. I plug in negative 2, that's going to go to 0. Negative 2 plus 3 is 1, so a is equal to 1. So I can rewrite my larger fraction into my partial fractions. So a is 1, so I have 1 over n plus 2 minus 1 over n plus 3. So now to write out the first few terms, I'm going to plug in a 1, so that's going to give me a 1/3 minus 1/4. There's my first term. My second term is a 1/4 minus 1/5. Plug in 3, so that's going to be 1/5 minus 1/6. My fourth term would be 1/6 minus 1/7, and so on. So now notice what's going to be canceling. I've got the negative 1/4 are going to cancel. I've got the negative 1/5 and positive 1/5. The only term that's not going to cancel is that 1/3. So I know this sum is going to converges by telescopic, and it converges to 1/3. So again, I've already got my two separate fractions, now I can write out my first couple terms. So if I plug in a 1, 1 plus 1 is 2, and 2 squared is 4, and then this is going to give me a 3 over 1. Plus, my second, 2 plus 1 is 3, 3 squared is 9, leave it unsimplified as 3/9, minus 3 over 4. plug in a 3. 3 plus 1 is 4, and 4 squared is 16. And then this is going to give me minus 3/9. So let's see what's canceling. I've got my positive 3/4 and negative 3/4. I've got my positive 3/9 and negative 3/9. So notice the only term that's remaining is going to be that negative 3. That's why you can't always just go by that first term. So I know it converges by telescopic, and it converges to negative 3. So those are your telescopic sums. A series we're really going to take a look at too in other sections is the harmonic series. So the harmonic series is one of the most important of all divergent series. And it arises actually with overtones produced by a vibrating string. So again, your harmonic series is the sum from k is equal to 0 to infinity of 1 over k. So here's your first few terms. We can see that the sequence is going to converge. But it's not obvious that the series converges or diverges. Just because the sequence converges, because remember we did convergence of sequences in section 9.1, does not automatically mean the series is going to converge. So although the divergence is slow, by using partial sums, the divergence will become apparent. The sum of the harmonic sequence is a subset of the sum of the values of the function 1 over x. So to show that the harmonic sequence converges, so here's my sequence. So again, remember how we show that we find whether or not a sequence converges. It's not alternating, but again, what I'm going to do is I want to find the limit as k goes to infinity of 1 over k, and that's equal to 0, and it converges. And it's converging towards 0. Remember, that's what the limit is getting really, really close to. We talk about a series, remember we're adding up all the terms. We're not talking about what we're getting really, really close to. We're adding all those terms together. So if you take a look at the graph of 1 over k, or 1 over x, remember we're adding all these terms together. What's happening is the graph is not getting close enough, fast enough to the x-axis to say that this series is converging to 0 as well. So we can prove this by finding the area under the curve. So again, if I do my improper integral going from k is equal to 1 to infinity, on my lower bound of 1 to infinity, of 1 over x dx. Remember we did improper integrals back in chapter 7. So remember the way we dealt with our improper integrals is I'm going to rewrite that upper bound, the limit, as b goes to infinity from 1 to b of 1 over x dx. So when I integrate, I have the limit as b goes to infinity, and the integral of 1 over x is the natural log of the absolute value of x. And again, I need to evaluate this from my upper bound of b to 1. So I want to find the limit as b goes to infinity of the natural log of b minus the natural log of the lower bound, which is 1. Again, I know natural log 1 goes to 0. So the question is what's happening with the limit as b goes to infinity of the natural log of b. Remember the graph of your natural log function? It's approaching infinity. So therefore, this series is going to diverge. So your harmonic series diverges, however, the harmonic sequence converges.